Everyone see that and hear me?
Yes.
Awesome. Hi everyone. My name is Devanshi. If you don't already know me, I work at the Wishart Lab in the CSIS building. My primary project is building the artificial gut. And so today, I'll be talking about something that comes up constantly in nutrition and health conversations, which is artificial sweeteners. So more importantly, how they interact with the gut and metabolic health. So, artificial sweeteners are everywhere now. They're often marketed as the healthier alternative to sugar. But the real question is, are they just harmless substitutes or do they have other biological consequences as well? So, throughout this talk, I'll look at some of the most common artificial sweeteners, why they're used, and what happens to them in the human body, and what research is currently suggesting about these. To start off, we know that excessive sugar intake has been linked to a wide range of health concerns. Things like type 2 diabetes, obesity, dental issues are some of them. So naturally, we gravitate towards alternatives that help us mitigate those types of health responses. That's where artificial sweeteners kind of come in. These are compounds designed to provide sweetness without the caloric load of sugar. Most commonly, they're seen in products like diet sodas, but artificial sweeteners are also found in some protein powders, sugar-free desserts, flavored yogurts, chewing gum, and actually even some medications. So we want to know that people consume these sweeteners daily without really thinking about it. And if they even reduce their sugar intake, what might be the effects of these artificial sweeteners too? So why are artificial sweeteners so commonly used? The first and most simple reason is that they provide sweetness with little to no calories, especially when compared to sucrose or sugar. Second, these compounds are incredibly potent. So a small amount of these, they're hundreds, almost 200 to 600 times sweeter than normal sugar. So you only need a tiny amount to get the same type of effect. Third, artificial sweeteners generally do not contain the same immediate spike in blood glucose that sugar does, which is why they're often used to manage diseases like diabetes. They're also widely help to help people reduce overall sugar intake, while still enjoying sweet flavors. And most artificial sweeteners have FDA approval and are usually safe to use. So that makes it easier for a consumer to go ahead and use these. So there's lots of different types of artificial sweeteners that do exist, but today I'll focus on the most common four types. So the first is sucralose. This is a chemically modified form of sugar and it's heat stable, so it's often used in baked goods and protein powders. You might know it more commonly as Splenda. Um, the second one is aspartame. This one is not that heat stable and it's made from amino acids, so it's more commonly used in diet sodas, drink mixes, or chewing gum. The third one is saccharin, one of the oldest and most used or artificial sweeteners. It's extremely stable and used in products like Sweet and Low or those little packets that you see when you go to a coffee shop for sugar alternatives. Um, and the last one that I'll talk about is asulfame K, potassium or ACE K. This one's often used in combination with other sweeteners, usually in energy drinks or supplements. And while all of these provide sweetness, they differ a lot in their chemical structure and how our human body processes them. So before I get into how artificial sweeteners impact our bodies, I think it's important to know about the microbiome. This slide is sort of a simplified view on major microbial groups that are in the human gastrointestinal tract. The first key point is that the gut is overwhelmingly made up of bacteria. So 98% of microorganisms belong to a few dominant bacterial types, while only a small portion, around 2%, is made up of other microorganisms such as fungi or viruses. So with those dominant bacterial groups, there's three major phyla that make up most of the gut community. The largest portion is firmicutes, which make up about 30 to 50%. This group involves fermentation and energy extraction from your food. The next major group is bacteroidetes. Usually this is around 9 to 40%, and they include some complex bacteria that have a role in breaking down complex carbohydrates and producing metabolic byproducts that we usually see. Finally, a smaller but a significant group is the actinobacteria, which range from about 1 to 13%, and these are often beneficial microbes linked to gut health. So overall, the gut microbiome is a highly structured ecosystem, and it's dominated by a few major groups, but it's often the balance between these groups that is important for normal metabolism, immune regulation, and also gastrointestinal function. So with that baseline in mind, we can look at how dietary exposures to artificial sweeteners can affect this balance and disrupt and shift these populations that influence both gut health and metabolic outcomes. So I'll start with sucralose. This is one of the most widely consumed artificial sweeteners today, and again, more commonly known as Splenda, if you've heard of that. So sucralose has a interesting origin story because it was discovered by accident. In the 1970s, scientists in the UK were working on chemically modifying sugar to understand how chlorinated compounds interact with biological systems. And one of the graduate researchers misheard the instruction to test instead of taste. And so it's a cool discovery, but I highly recommend no one taste anything in the lab ever. But it did lead to the discovery of sucralose. So sucralose is chemically derived from sucrose. So this is the chemical composition of sucrose. The difference between sucralose and sucrose is the several hydroxyl groups that are replaced with chlorine atoms. This modification makes it much sweeter than sugar, heat stable, but also resistant to breakdown. This is why it's used more commonly in baked goods and protein powders. For a long time, sucralose was considered biologically inert, which they thought it was simply meant to pass through the body, but recent research shows otherwise. So, some studies show that when sucralose is consumed alongside a carbohydrate-rich diet, it may contribute to decreased insulin sensitivity. This is important because insulin sensitivity is central to metabolic health, and artificial sweeteners are often chosen specifically to improve glucose control. Additionally, people with type 1 diabetes who consumed sucralose combined with ACE-K had been linked to an increased GLP-1 secretion. So GLP-1 is a gut hormone that's involved in insulin release and appetite regulation. So this suggests that sucralose may influence endocrine signaling as well, not just sweetness perception. So, sucralose in the gut is largely unmetabolized. It passes through the gastrointestinal tract without being broken down by gut microbes. So, the important part of looking at studies with sucralose is that the formulation matters. There are some studies that do research with 100% sucralose, and there's others that use tabletop variations of sucralose. This is important because some of these include maltodextrins, which can change how sucralose reacts in the gut. So, keeping that in mind, some of these studies that were done with sucralose show, in mice at least, a microbial dysbiosis. So, in animal models, especially mice, sucralose exposure has been associated with microbial imbalance or dysbiosis, but also some mouse studies report metabolomic effects that have increased liver cholesterol or changes in bile acid profiles, such as cholic acid, increasing that. We don't exactly see the same effects in humans, though. Human studies show more mixed outcomes, but usually it shows a shift in gut microbiota composition, particularly when sucralose is administered with glucose as well. So, despite some slight microbial changes that are seen in humans, short-chain fatty acids, which are key fermentation products in the gut, are not always significantly affected by sucralose or aspartame in human trials. Interestingly, we didn't see a huge shift in the gut microbiota, but they saw a shift in oral microbiome switches. So, beyond the gut, a study in 2022 observed changes in six streptococcus species in the oral microbiome. Finally, sucralose has been linked with some studies to a higher glycemic response compared with glucose alone and suggests potential impact on glucose regulation as well. So moving on to aspartame in the human body. This is another extremely common sweetener found in diet sodas and drink mixes. Also coincidentally found accidentally. Don't taste things in the lab. The chemical structure is unique because it's composed of two different amino acids, aspartic acid and phenylalanine, with a methyl ester group. So this makes it almost 200 times sweeter than sucrose. So this diagram shows the breakdown process of aspartame in the body. Unlike sucralose, it does not remain intact in the digestive system, so it undergoes hydrolysis almost immediately. So when you ingest aspartame, it breaks down into phenylalanine, aspartic acid, and small quantities of methanol. So this means that very little of the parent compound of aspartame is found in your circulation. There is a safe, acceptable daily intake or ADI for aspartame. It's about 50 milligrams per kilogram body weight in the United States and slightly lower in the European Union. However, most humans fall way under this limit, so usually this limit isn't a big issue. The problem comes for individuals with phenylketonuria or PKU. Patients with PKU cannot metabolize phenylalanine properly, which makes this a dangerous product. This is why a lot of products that do contain aspartame have warning labels on them to make sure people are aware. So, in rat studies, aspartame has been shown to reduce overall calorie intake, limit weight gain, improve body composition, particularly under very high fat diet conditions. However, other findings suggest that metabolic downsides. Aspartame increased fasting blood glucose and reduced insulin stimulated glucose disposal in rats, even on both standard and high fat diets. However, high-fat diets by themselves cause major microbiome shifts, including a decrease in bacteroidetes and an increase in firmicutes, which is a common pattern linked to obesity-related dysbiosis. Now, in humans, aspartame and other sweeteners have been reported to alter intestinal microbiota composition and affect microbial function compared to control groups, but there isn't quantitative data on that that I saw. Again, this one had oral microbiota shifts as well, rather than the gut. There were reductions seen in some species of the oral microbiome. So one of the oldest forms of artificial sweeteners, saccharin, was found in 1879, so a long time ago. This was before it was found to replace sugar. It was, again, accidentally found, and it was more of introducing the concept of sweetness without actual sugar. It became really popular during the World Wars for sugar shortages as well. So saccharin is interesting because it does not undergo significant gastrointestinal metabolism. In humans, 85 to 95% of it is absorbed fully intact. It circulates unchanged and then is finally excreted out through urine. So for years, it was assumed to have minimal biological impact. Um, in mice, there was an altered microbiome bacterial ratios. So we saw shifts in the balance and ratios of bacterial groups in the gut microbiome. Rats that had a chronic that were given saccharin for 6 months, they saw long-term effects like inflammatory effects. They showed an increase of expression in hepatic pro-inflammatory genes like inducible nitric oxide synthase and TNF alpha with statistical significance. However, in humans, saccharin has also been linked to microbial changes in the oral microbiota as the other ones. But it's also seen to raise glycemic response compared with glucose-only groups and no supplement groups, suggesting potential impacts on glucose regulation. Last but not least, we have ace-sulfame K, or ACE-K, was also discovered in the late 1900s, also accidentally. Seems to be a theme of all of these. And ACE-K is the potassium salt of an acidic cyclic sulfonamide. It's popular because it has no calories and it's very stable. It also blends well with all the other sweeteners, so it's often used as an enhancer as well. That's why it often appears in energy drinks or supplements and sugar-free candy. So ACE-K is almost absorbed entirely in the small intestine. So unlike sugar or even aspartame, it undergoes no metabolism. More than 99% of it is excreted unchanged in the urine. So this shows that it has minimal biological impact. However, in mice, we saw a very sex-dependent result of ACE-K treatment. In male mice, it was shown to have a strong increase in bactericides, along with significant changes in other species. In female mice, it was a bit more broad. ACE-K dramatically lowered relative abundance of different types of um, bacteria, including unassigned groups that we see, and also increasing some bactericides instead of decreasing, which was interesting. These microbial differences also align with metabolic outcomes. ACE-K increased body weight gain in male mice, but not in female mice. In humans, however, we don't see the same strong shifts. In clinical data, bacterial abundance profiles were not significantly different, which showed a difference between mice models and human studies, and overall effects of the microbiome were actually minimal. So, after all of these, looking into them, there are a lot of limitations. A lot of studies are done primarily on mice or animal models. This helps us see the long-term effects of them, but they're not always physiologically relevant to human studies. I think that more human studies are needed to really see the effects of these. That being said, oh, there have been some long-term studies done on the human effects of all these artificial sweeteners as well. So this long-term study was done in France with over 100,000 human participants, and it was carried over 2009 to 2022. So these people were exposed to artificial sweeteners, and their diet was kept track of. It was using all four sweeteners that I mentioned today. Um, and what makes this study really strong is that it used repeated dietary records and detailed additive databases. So it allowed researchers to estimate sweetener intake across all different types of food sources. Interestingly, they found positive associations between artificial sweetener consumption over a long period of time and increased risk of type 2 diabetes. That being said, this doesn't mean that correlation is causation. People who consume high diet products like artificial sweeteners may already be at a higher risk for things like type 2 diabetes, so it's not always that artificial sweeteners may cause this. However, a positive association was seen, so it raises important concerns when it comes to mechanistic microbiome studies and looking at the metabolism of all of these artificial sweeteners. This is mainly why artificial sweeteners remains an active research topic still, and is quite controversial to this day, whether on how good it is or how bad it is. Um, that being said, the main takeaway of this presentation is not to say one is better or worse. There's both pros and cons to all the different types of artificial sweeteners, as well as replacing sugar with these artificial sweeteners. But the main point of this is to inform everyone and to know what products contain what kinds of artificial sweeteners. Hopefully, it's one more ingredient that you understand on the list of chemicals that you see. Um, Focusing on moderation rather than avoidance is very important, and making an informed decision about consumption. Make sure you know what you're consuming, what you're putting into your body, and how it affects your health can be really great. That being said, I wish everyone a sweet Valentine's Day, whether it's organically or artificially, and I can take any questions if there's any. Thank you so much.